Hi, I am Cohen, and I'll talk about efficient candidate screening under multiple tests and implication for fairness. This is a joint work with Zach Lipton and Yishay Mansour. Let's start with some motivation for candidate screening. Say an employer would like to hire candidates for jobs. Of course, she is only interested in the skilled ones. Also, we assume that the hiring cycle is endless. So think about a big enterprise that never stops recruiting employees. Now, the problem is that given a candidate, the employer cannot observe his underlying skill level. Instead, she can only estimate it by performing a series of tests. This introduces a trade-off between the quality of the signal, which requires many tests for accuracy, and the cost of the interviews, as employers prefer to minimize the number of interviews or tests in order to save costs. Now, before we continue, let's review some related work. Our model is mostly inspired by a line of research in economic literature, which is called statistical discrimination. In these works, there are candidates with unknown qualities and a single test result, which is the only signal about them, and it is characterized by a group-dependent noise level. In contrast to these works, our work involves richer mechanism. In fact, we optimize the signals. What about CS? There is a growing line of research that regards fairness in machine learning, in which the task of binary classification is considered, where candidates are characterized by protected and unprotected features. And the goal is to get an accurate prediction that would also satisfy one or more fairness notions, such as demographic parity, blindness to the protected features, and equalized false positive or false negative rates. In our work, there are two types of models. First, we'll discuss the Bernoulli Model, in which there is an infinite pool of candidates. Each candidate I has a binary skill level yi, which is sampled from a Bernoulli distribution with a known parameter p. Once it is sampled, the skill level of a candidate is fixed and does not change stochastically. So each candidate is either skilled, hence yi equals 1, with probability p, or unskilled with probability 1 minus p. Now, after we have established that each candidate has an underlying skill level, which of course remains permanent, we can start talking about tests. We assume that there are binary tests, 0 or 1, fail or pass. Unfortunately, tests aren't perfect. Each test has a fixed probability of flipping the skill level of a candidate. So a skilled candidate can be observed as a candidate who failed the test and the other way around. The noise level is determined by a noise parameter denoted by sigma, which is also known. Now, notice that noise is symmetrical. The probability that a skilled candidate fails a test is the same as for an unskilled candidate to pass it. Now we can evaluate candidates based on a series of independent tests. how does an employer should decide whether to hire someone? We look into two types of policies. First, the threshold policy, which has a fixed number of tests per candidate, no matter what are the intermediate test results. It accepts candidates if and only if they passed at least theta out of tau tests. On the other hand, there is the dynamic policy, which reevaluates candidates after each test and decides whether to accept, reject, or simply keep on testing. In this policy, the number of tests becomes a random variable. Let's move on to some optimization objectives. We start by attacking the problem from a classic ML perspective. We wish to minimize false positives, the number of unskilled candidates that were classified as skilled, and false negatives, number of skilled candidates that were classified as unskilled. And of course, if we want to use the threshold policy, we would have to balance them, as a high threshold theta results in a low false negative rate, but high false positive rate, and low theta threshold results in low false positive rate and high false negative rate. So given a candidate and his test results, we introduce an alpha loss, parameterized by alpha between 0 and 1. And for each parameter alpha, we are interested in the policy that minimizes the expectation of the alpha loss. Now we can properly define the task. We are given with skill and noise parameter P and sigma, a parameter that determines how much we want to balance between false positive and false negative, which we call alpha, and a fixed number of tests, tau. The output is a threshold, the number of tests out of tau that a candidate should pass in order to be accepted by pi. So in this case, we can show the loss function L alpha of theta is quasi-convex and derive the optimal threshold as a function of all the input parameters. This is the result that we would expect, as when P equals half and alpha equals half, meaning that each candidate has an equal probability to be skilled or unskilled, and the loss is set that we equally care about false positives and false negatives, the optimized threshold would be a majority rule, as this term here would be 0. But how many tests do we actually need to get an accurate prediction? So for example, if we want majority, in order to bound the loss by delta, we need at least 1 over sigma square ln of 1 over delta tests for any parameter delta between 0 and 1. And the question is, can we do better? To answer this question, let's introduce some more objectives. First, there is the false discovery rate, which is the fraction of unskilled candidates accepted by the policy. We can also think about it as the false positive rate over the probability to be accepted. Similarly, we can define the false omission rate, which is the fraction of skilled candidates that were rejected by the policy. Or we can just think of it as false negative rate divided by the probability to be rejected by the policy. So let's enhance our optimization problem in a way that the optimal policy would also have an optimal fixed number of tests. So for this, I want you to consider a budget parameter B, which is greater than 1. We still have our noise parameter sigma, meaning that the noise level is 1 minus sigma over 2. And we also consider balanced groups. Balanced group of candidates, meaning P equals half. Now, if we think like an employer, we would like to find a policy with false discovery rate as low as possible. We don't want to hire the unskilled candidates. We also would like to have a constraint such that the expected number of tests per hire is never larger than B, the budget parameter. This is exactly the trade-off I talked about in the beginning of this presentation. So for this, we have shown in the paper that for any set of parameters, we can find an optimal policy, and that it would be a randomized threshold policy, where by random policy, we mean that if a candidate passed more than theta test, he is accepted. If he passed less than theta test, he is rejected, and whoever passes exactly theta out of tau test has some probability R to be accepted by the policy. Now let's see an example for this. Say B equals 18 and the noise level is third. In this case, the optimal threshold policy is to hire someone if and only if he passed 3 out of 3 tests. There are 2 issues with this policy in this example. First, candidates who failed the first or second test would have to go through more tests for nothing, as they would be rejected by the policy anyway. Second, let's imagine a candidate who passed 2 out of 3 tests. This candidate is rejected by the policy, even though he is more likely to be skilled than any other freshly sampled candidate from the pool. The problem is that if we change the policy to accept candidates who passed 2 out of 3 tests, we increase the false discovery rate. So the solution is to keep testing these candidates that seems more likely to be skilled than untested candidates. This brings us to the greedy policy, which would be dynamic. So the greedy policy goes like this. We keep on testing as long as the posterior probability that a candidate is skilled, given his test results, is higher than the probability that a new candidate from the pool is skilled. And as long as the posterior probability is smaller than 1 minus epsilon, where epsilon is the desired false discovery rate. Now, if we also want a low false omission rate, for example, that it would be lower than P, we can just keep on testing as long as the posterior probability is between epsilon prime and 1 minus epsilon, where epsilon prime is the desired false omission rate. So how do we analyze a policy which does not have a fixed number of tests? We reduce the problem to gambler's ruin, which is a one-dimensional random walk with absorbing barriers, and it goes like this. The starting point of each candidate is the prior log odds. After each test result, the candidate moves 1 step to the left in case he failed the test, and 1 step to the right in case he passed the test. Since the probability of a flip are equal for skilled and unskilled candidates, our random walk has a fixed step size. Also, our reduction makes sure that the lower absorbing barrier matches the case where the posterior skill level dips below the prior skill level, and the upper absorbing barrier matches the case the posterior probability is that the candidate is unskilled is lower than epsilon. This allows us to derive several results. First, we showed the greedy policy minimizes the expected number of tests under the false discovery rate and the false omission rate constraints. So this is indeed an optimal policy. Second, we can calculate the expected number of tests based on the input parameters. And third, we can get a confusion matrix, which will depend on the input parameters and would have a low false positive rates. Okay, so epsilon is a parameter that is determined by the employer, and of course employers would like it to be small, and the false positive rate is even lower than that. Of course, the expected number of tests would increase when epsilon is smaller. If we also want a low false omission rate, we can set the rejection to be epsilon prime and get a similar result regarding the false negative rate. So let's say we have two groups of people, blue and red. And let's say both of them have the same skill level parameter, P, but different noise levels. The red group has a higher probability for a flipped test result. This might be due to unfamiliar recommendation writers, unfamiliarity with the grading standards in their university, or any other reason that might arise when we are testing candidates for minority population. Now, an impossibility result emerges. If we use the same policy, whether it's threshold or dynamic for both groups, what ends up happening is that G2, the red group with the higher noise levels, would have higher false positive rates and higher false negative rates. So how can we fix it? How can we make the policy to be more fair? This is where we can wield the power of the dynamical policy to achieve fairness. We can equalize false positive rates and false negative rates by giving more interviews to people from the red group, which is noisier. So for example, if we set epsilon to be the ratio between the sigma of the blue group and the sigma of the red group, we can get the same level of false positive rate. This is still not a magic solution, as it will require people from the red group to do more interviews, more tests. But on the other hand, it will yield the same confusion matrix entries for both groups. So up until now, we assume that we already know in advance the parameters P and sigma. Now we introduce an unsupervised parameter estimation for these P and sigma. And surprisingly, we don't need a single ground truth label in order to evaluate them. It goes like this. Assume we have at least 2 test results from n different candidates from each group. Now, we can simply estimate P of a group and sigma as follows. We denote by C the percentage of candidates in the dataset with inconsistency in the first 2 tests. We know that this number can be viewed as a Bernoulli random variable, with this as a parameter. And now we can extract an estimation for sigma. We denote it by sigma hat. The same goes for P. Let P denote the percentage of candidates with positive first test. We already know what is the parameter that this P is generated from. This is exactly that. Now we can plug in sigma hat and extract P hat, our estimation for P. Finally, we can use Chernoff bound to derive the needed number of candidates from each group to get a good estimation of the parameters. Okay, so in the beginning of the talk, I mentioned that there are two models in our work. Here comes the second one. In the second one, there is a Gaussian model, similar to the one in economic literature. In this model, a worker's quality Q is normally distributed with mean parameter mu Q and variance sigma Q squared. So now, instead of binary skill level, we have continuous quality. As for the noise, conditioned on this Q, a test is generated by adding noise to the quality, where the noise is once again symmetrical and sampled from a normal distribution with mean parameter 0 and some variance parameter, which we also know. By the way, there is also an unsupervised parameter estimation for this model as well. So for this model, we also have an impossibility result. That is, if we use the same policy for two groups with different noise levels and the same quality distribution, we get worst false positive rates and false negative rates for the noisier group. As for the solution for this, we can once again increase the number of tests for the noisier group by multiplying the number of tests in the ratio between their noise variances. Okay, so let's sum up. In this work, we assume that when a candidate arrives, we already know which group he is from. We know we can estimate P and sigma of his group. And then the optimal thing to do is to use the greedy policy in a way that the false positive rate and the false negative rate would be the same across all groups that we test candidates from. We also know that this is the most efficient thing to do. To finish, I would like to discuss implications for fairness. Let's say we have two groups and the same number of tests, and consider the same decision rule for both groups, as it is in many companies. What would happen to the noisier group? It would have higher false discovery rate in any policy, as we have demonstrated. This might lead to higher rates of people that are fired from this group, since when unskilled candidates are hired, they are very likely to end up being fired. Later on, employees might erroneously conclude that this group skill level is lower than it actually is, and the process would keep reinforcing itself. Instead, we suggest to use another kind of policy, the dynamic one that gives candidates from different groups a different number of tests and is able to handle these issues. This comes at a cost of more tests for candidates for candidates from the noisier group, which, in our opinion, are more reasonable cost than the alternative. So that's it. Thank you very much for listening.